Hello students, so hope you all are doing fine and preparing good for your upcoming examinations. So today we will be discussing of the topic like under the subject mass transfer, like dimensionless numbers that are used in mass transfer. So we will focus only on the dimensionless numbers which are involved or which we tend to use in our mass transfer subject. Okay, and then at last we will also look over the mass transfer analogies. There are two analogies, we will just look over that. So let us start. Yeah, so the first number that comes to our mind, that is it involved in fluid mechanics also, heat transfer also, or we have been studying this number since our childhood only, since our +2 level. So this number is the Reynolds number. So by the basic definition we know that the Reynolds number is equals to inertia force divided by viscous force, and we also know that by just simply writing it, this comes equals to as rho v LC divided by mu. Okay, so we will just look forward that how we get this formula. Okay, we know that it's just nothing, it just tells us about the relative importance between the inertia force or the viscous force. Or suppose a flow is happening through a pipe, so by the virtue of the Reynolds number of the flow we can determine that whether the flow is laminar or turbulent. Okay, so let us see that how to derive our Reynolds number. So by basic definition we know that Reynolds number is our inertia force divided by the viscous force. So what is our inertia force? Our inertia force is always equals to mass into acceleration, that is mass into acceleration. Okay, now this mass into acceleration, we consider that what is mass? Mass is density into volume. So suppose we are writing density as rho and volume, that is LC cube. Now how we can write the volume about LC cube? So the number is a dimensionless number, so we will mainly focus on the dimensional analysis of our quantities. So what is the dimension of the volume? Meter cube. And what is the dimension of LC cube? It is also meter cube. So like this we define, like mass will be rho into LC cube, that is our mass, that is our density into our volume. So this gives our mass, and our acceleration will be there. So acceleration we know it is velocity upon time, so we will write it as velocity upon time. Okay, so this is our inertia force. Now if we go a little bit forward and we will discuss our viscous force. So what is our viscous force? So we know that viscous force is equals to F. Now this F is equals to our tau into area, that is tau into area, where this tau is defined as our shear stress. And what is the formula of the shear stress? That is mu into du by dy. This we get from our Newton's law of viscosity. Okay, so let us write it in our in the dimensionless term. So mu will be written as mu only, that is our dynamic viscosity. This du we can write it as velocity, and this dy we can write it as LC. Okay, so this turns out to be tau, and our F will be equals to tau into area. So it turns out to be mu into V divided by LC and into area, that is LC square. Okay, so this is there. Now we have got the expression for our inertia force, and also we have got the expression for our viscous force. Okay, now let us derive the equation for our Reynolds number. So Reynolds number, that is REN, was equals to inertia force, that is rho LC cube V by T, and divided by our viscous force, that is mu V by LC and into LC square. Okay, now let us see what gets cancelled out. This LC and this one LC will get cancelled, and nothing else is getting cancelled, no? Okay, one LC here and one LC here will get cancelled, so it will turn out to be LC square. Yeah, okay, and one velocity here and one velocity here, it will get cancelled. Okay, so what we are getting is as rho LC square divided by time and divided by mu. We are getting it like this. Okay, now we also know. Okay, so what we got? We got we got REN to be as rho LC square divided by time and divided by mu. Okay, so we know that the unit of velocity is what? Meter per second. So that means we can write velocity as LC per unit time, matlab LC by T. So it will turn out to be rho into LC divided by T into LC and divided by mu, and this in turns to be as rho into V into LC and divided by mu. So this is the final expression of our Reynolds number, which we tend to use everywhere. Okay, so its derivation is not that much important from the gate point of view, but conceptually, means if we go through the concept, so this derivation must be known to all the chemical engineers conceptually. Okay, and you know that in this short concept series that has been started by EII, so we just discussed about the concepts that are not much highlighted, that are not much highlighted in general, so we focus on those concepts. Okay, so we have got the expression for the Reynolds number, that is rho V LC by mu. Now let us move forward to another dimensionless number, that is Schmidt number. So Schmidt number is momentum diffusivity divided by mass diffusivity. Okay, it is momentum diffusivity divided by mass diffusivity, and its general that is there. It has the relative importance between the momentum diffusivity and the mass diffusivity. Just simple discussion. So we will look about that. What is the formula for this? Okay, what is the formula for this? We will just look out for this and how we derive the formula. Okay, so first of all, let's start with Schmidt number. So what was Schmidt number? It was momentum diffusivity divided by mass diffusivity. Now momentum diffusivity means nu, kinematic viscosity. Kinematic viscosity and the momentum diffusivity are both the same terms, and nu is defined as this nu. It is defined as mu, direct dynamic viscosity, divided by rho. So this gives us our momentum diffusivity. This is what? This is our momentum diffusivity. Yes. Okay. Now if we look forward to what is our mass diffusivity, so mass diffusivity, we know that mass diffusivity is represented by DAB, that is diffusivity, and this unit is meter square per second, and kinematic viscosity or momentum diffusivity unit is also meter square per second. So unit get cancelled, this becomes a dimensionless number. So Schmidt number will be defined as mu by rho and divided by DAB, which turns out to be mu divided by rho DAB. Yeah, so this is the final expression, like SCN, Schmidt number, is equals to mu divided by rho into DAB. Yeah, this is the final expression for our Schmidt number. Okay, now let us move forward and look into another dimensionless number. Yeah, this is our PECLET number. Okay, so this PECLET number, what is it is? This PECLET number is defined as the advective mass flux and the conductive mass flux. Okay, now let us understand that what is defined as the advective mass flux. What is advection? So we generally come across the terms that is convection or conduction, but advection is not. That is, we generally don't come across the term advection. So what is advection? Let us understand that. Okay, advection. So suppose, what is advection? In simple language, suppose there is a beaker and we have placed a sugar cube here. Okay, and we have it is filled with water and we have placed a sugar cube here. So mass transfer here will take place. If we don't disturb this system, so slowly the sugar molecules will dissolute and create a heavy density solution here, and the concentration of the sugar molecules is less at the top. So because of this concentration difference, the mass transfer will take place. The sugar molecules will travel from here to here and from here to here. Okay, this thing will take place. This is known as conduction. Simply it is known as conduction. Okay, now simply if the same system is there, what is there? The same system is there. Suppose the same system is there. And what we are doing is that we are just taking a spoon and stirring it. We are just taking a spoon and stirring it, or we are adding motion to the system. So what will happen? Convection will take place. This will be a case of the forced convection, that we are adding motion to it, we are stirring it. As a result, these sugar molecules will go here, and these water molecules will come here. It will create a mixture much faster than the conduction. So this is the case of the convection. Okay, now let us see about advection. Now what is advection? So advection is the type of mass transfer. Advection mass transfer is the type of mass transfer that takes place due to the motion of the medium itself. Due to the motion of the medium itself. What I am supposed to say is that, suppose this is a beaker, it is filled with water, and we are placing a sugar cube here. We are not stirring it. What we are doing is we are just tilting the beaker. We are just tilting the beaker. So what will happen? Water will flow. Suppose this is a table. So the water will flow. The water will flow and spread out. The water will flow and spread out. And what will happen also? The sugar that dissoluted and created a high concentration zone here, the sugar molecules will flow. Yeah. And this is not the case of the convection. This is the difference between the convection and the advection. So this is the case of the advection, where the mass transfer occurs due to the motion of the medium itself. Okay. Okay, so let us come back to our topic. Just a small explanation I needed to give you, as because advection is not a common term that we generally come across in our daily life. Yeah, convection and conduction is clear, but advection generally we don't come across. Okay, so Peclet number is nothing. It is just defined as the Reynolds number into Schmidt number. Okay, Peclet number is what? It is just Reynolds number into Schmidt number. Okay, now let us move to the next number. What is the next number? Yeah, it is the Stanton number. So Stanton number is what? Convective mass flux divided by advective mass flux. So how we will define it? So we define Stanton number. We define Stanton number of mass transfer as Sherwood number and divided by Schmidt number into Reynolds number, or we can also write it as Sherwood number divided by Peclet number. Now what is Sherwood number? That we are just going to look into it. It is just in the subsequent slides, so don't take attention about that. Just remember that Stanton number is equal to Sherwood number divided by Schmidt number and Reynolds number. Okay, now let us look forward about what is Sherwood number. Okay, because that is important na? Yeah, here comes the Sherwood number. So what is the definition of the Sherwood number? The definition of the Sherwood number is convective mass flux divided by the conductive mass flux. Okay, so what is the convective mass flux? What is the convective mass flux? Convective mass flux we define as mass transfer coefficient into concentration difference. That is, let us write it about delta Ca. Okay, this is our convective mass flux. And conductive mass flux, how is conductive mass flux defined? Through Fick's law of diffusion. So what it is? dAb into delta Ca minus dAb into dou Ca by dou Z, that is delta Ca, and divided by, we can write it as Lc. We can write it. So from here this will get cancelled, and it will turn out to be as Kc into Lc divided by dAb. So this is the formulation of our Sherwood number. It is Kc into Lc divided by dAb. Clear? So this is Sherwood number. Now let us just look forward into the next topic, and that is, okay, one more thing. The relation between the Sherwood number, and the Reynolds number and the Schmidt number, it is such like, it is like this. See, it is like this. Like Sherwood number is generally A plus C Re to the power, suppose m, and Sc to the power n. Okay, this is the mathematical formulation of our Sherwood number generally for a system. Okay, this is Reynolds number to the power A is constant, C is constant, m and n both are constant. Reynolds number, Re represents Reynolds number and Sc represents Schmidt number. Okay, so Sherwood number equals to A plus C into Re to the power m and Sc to the power n. And in cases, and for sphere, just for sphere, it helps in the numericals. Just for sphere, this the value of this A is equals to 2. Just for sphere, the value, I will write it clearly. Yeah, just for sphere, the value of this A is equals to 2. Okay, now suppose a system is given which is a stagnant system, means conduction mass transfer is happening. It is a stagnant system. In that stagnant system, the value of the velocity will be equals to 0. Now once the value of the velocity is equals to 0, that means this Reynolds number will be equals to 0. If Reynolds number is 0, then this entire terms becomes 0. This entire term becomes 0. Now once this entire terms becomes 0, so we are only left with the A term. So our Sherwood number will be equals to only A, and in case of a sphere, it will be just equals to 2. Yeah, in some numericals you might have, by preparing while solving the previous year questions, you might have come across the question like that a spherical ball of benzene is been suspended in a water beaker, and the benzene is diffusing. Okay, so there is no velocity, it is a stagnant medium. In a beaker it is kept, it is a stagnant medium, there is no velocity. So once there is no velocity, so the Reynolds number will be equals to 0, the Sherwood number will be equals to 2, as because it is a bending sphere, and for sphere the value of A is equals to 2. Okay, so in that case we get directly the value of the Sherwood number, and Sherwood number is equals to mass transfer coefficient into characteristic length divided by diffusivity. So from there, maybe we know the diffusivity, we know the characteristic length. The characteristic length of the sphere will be its diameter, so we can calculate the mass transfer coefficient. So once we get the mass transfer coefficient, we can calculate the flux. Okay, so like this everything is related, and like this Sherwood number helps us in calculating the mass transfer coefficients. Okay, so let us move forward and let us look into the next topic. I think it's the it's a Lewis number. So what is Lewis number? By definition, what it is written, Lewis number is defined as mass thermal diffusivity divided by mass diffusivity. So thermal diffusivity means alpha. Thermal diffusivity means alpha. Let me write it. Yeah. So thermal diffusivity. So thermal diffusivity is generally defined as the alpha. So what is alpha? It is thermal conductivity divided by rho into Cp, that is heat capacity. And mass diffusivity, you know, mass diffusivity, there is no right to write, but still okay, I am just writing it. Mass diffusivity is equals to DAB. Yeah. So from here our Lewis number, it will turn out to be thermal diffusivity, that is alpha, and divided by DAB, that is mass diffusivity, and this alpha in turn is defined by K divided by rho Cp and divided by this DAB. Clear? So the general formula which comes out, it comes out to be that Lewis number is equals to, it was K divided by mu, no mu, it is rho. Lewis number divided by rho Cp and DAB. Okay. Yeah. So this is our Lewis number. Now let's look forward. And yeah, the next topic is the mass transfer analogies. So there are two mass transfer analogies. The first one is the Chilton-Colburn analogy, and the second one is the Reynolds analogy. So we can say that this Chilton-Colburn analogy is for the general cases, and this Reynolds analogy is just a special case for the Chilton-Colburn analogy. Okay. So in general, the Chilton-Colburn analogy said that suppose this is the fanning friction factor F. This is the fanning friction factor F. So F divided by 2 will be equal to Stanton number of mass transfer and into SC to the power, that is Schmidt number to the power 2 by 3. Okay. So this in turn comes out to be, Stanton number is what? Sherwood number divided by Reynolds number into PECLET, Reynolds number into Schmidt number, and into Schmidt number to the power 2 by 3. Okay. So this is the relation, provides us a relation between the friction factor and the Sherwood number and all the dimensionless numbers. Okay. So like this is the relation. And what is Reynolds analogy? Reynolds analogy is just the special case of this, where special case where this SC is almost equals to the Prandtl number of the heat transfer, and which is almost equals to 1. Okay, when Schmidt number and the Prandtl number both are tend to equal, and both are almost equals to 1, okay, then this becomes the special case, and this formulation what we have got here, it will just convert into the Reynolds analogy. Okay. Yeah, so these were the mass transfer analogies. So we have discussed the dimensionless number. These are the these dimensionless numbers, and the concepts and the formulas and the derivation. These are enough from the gate point of view. Okay, and we'll then meet in our next lecture, where we will discuss unequimolar counter diffusion. Like equimolar counter diffusion is a general topic, it is a highlighted topic, but okay, but the unequimolar counter diffusion, it is a little non-highlighted topic, it is a little special type of topic, so we will look after that. Okay, but it's also important from the gate point of view. Questions may come. Okay, so thank you all. Hope you have enjoyed this session, and so we try to deliver all the topics which are not highlighted in this series of the short concepts from EII. So if you want any specific topic, you can comment it under the video. Okay, thank you.